Okay, let's unpack this. We're not just talking about, a marginal improvement in the world of computing.
No, not at all.
We are looking at a fundamental redesign of the core component of modern technology, the transistor itself. I mean, we are at a definitive inflection point, the end of the FinFET era.
Yeah, that architecture has powered our devices for, what, the last decade?
A decade, yeah. And it's hit a physical wall.
Mm-hmm.
And TSMC, well, they've just launched the replacement.
It's truly historic. You've really captured the tension perfectly there. I mean, we are witnessing the dawn of what's being called the Angstrom age.
The Angstrom age.
Exactly. TSMC, the foundry giant, has officially moved into volume production of its 2-nanometer process node, or N2. That started in Q4 of 2025.
And what makes this so significant, it's not just a size shrink, right?
No, it's the most profound architectural shift in transistor design since the vertical FinFET concept first even appeared.
And I think what gives this deep dive its urgency is the financial cost. I mean, this N2 node, it's not just for slightly faster phones.
Not at all.
It is the first process that's explicitly designed for the explosive demand of the AI supercycle.
Right, for that continuous high-intensity processing you need for what they're calling agentic AI systems.
Exactly.
And enabling that kind of power requires this generational shift, but it comes with a sticker shock that's completely rewriting the economics of Moore's law.
So today we're diving into the technical fixes, the crazy financial reality. I mean, an N2 wafer reportedly costs $30,000.
A staggering number.
And what this all means for companies like Apple and Nvidia, who need this tech not just to win, but really just to manage the basic thermal limits of their computers.
Right, so our mission is to understand why this technology is absolutely non-negotiable, even at that insane price.
Let's start right at that physical wall you mentioned. We relied on FinFET, that vertical three-sided fin, for so long. Why did it finally break down below the 3-nanometer mark?
It really came down to a problem of basic control. So think of a transistor as a switch.
Right, on and off.
Exactly. The gate material is supposed to pinch off the flow of current when the switch is off. But as those fins got thinner and the gate lengths got shorter, below about 3 nanometer, the gate just lost its grip.
It couldn't hold on.
It could only wrap around 3 sides, and so the current just started leaking, escaping around the edges. They call it parasitic leakage.
So the chip was just bleeding energy constantly, even when it wasn't supposed to be working.
That's it. And that leakage translates directly into wasted battery life and, for these 1,000-watt AI accelerators, waste heat. Just tons of it. The chips were becoming thermally unmanageable.
Okay, so what's the fix in N2? How does TSMC get that control back?
They moved to what's called a gate-all-around, or GAA, nanosheet transistor.
Okay, break that down for us.
To put it simply, instead of one single vertical fin, they use a stack of extremely thin horizontal silicon sheets, the nanosheets.
So it's horizontal now, not vertical.
Right. And critically, the gate material now completely surrounds these nanosheets on all 4 sides.
Ah, so if the FinFET was like a 3-sided fence trying to stop something,
Yeah.
the nanosheet is a fully sealed sandwich bag.
Yeah.
You get that 360-degree control.
That's a perfect analogy. That 360-degree control virtually eliminates that leakage because there's just nowhere for the current to escape.
And that means?
It allows the chips to operate reliably at a much lower voltage, or Vmin, which is the key to the huge power efficiency gains we'll get into.
Okay, so that solves the leakage.
Yeah.
But one of the most exciting things I found in the sources was the flexibility this gives chip designers. Something called nanoflex.
Yes, nanoflex is a massive architectural advantage. I mean, with the old FinFET rules, if you needed a block of logic to be faster, to carry more current,
You had to add more hardware.
you had to add an entire discrete fin, which meant these big, inefficient jumps in size. With nanosheets, designers can vary the width of the horizontal sheets continuously during manufacturing.
Wait, continuously?
Yeah.
So they can literally dial in the exact performance they need for different parts of the chip.
Precisely. They can fine-tune that trade-off. Wider nanosheets for, say, a critical CPU core that needs high performance.
The narrower ones for something else.
Exactly. Narrow sheets to save power and area for a less sensitive block, like a memory controller, all on the same piece of silicon. It's a level of precision they just never had.
That's a fundamental change in chip layout. But the transistor is only half the battle. If you solve the switching, what about the plumbing? The wires connecting everything.
You're right, you just moved the bottleneck. That's where the back end of line innovations come in. As those tiny copper wires get thinner, resistance skyrockets.
Which would just cancel out the power gains from the new transistor.
Completely. So TSMC had to introduce a new low-resistance redistribution layer, or RDL, just to maintain conductivity.
And what about managing the power draw? We're talking billions of transistors switching at once.
Yeah.
That must create huge power fluctuations.
It does. It's a huge problem called voltage droop. To fix it, they had to integrate these things called super high-performance metal insulator metal capacitors, SHPMs.
That's a mouthful.
It is, but think of them as tiny shock absorbers or little batteries built right onto the chip. They offer more than double the capacitance of the last generation.
So they act as local reservoirs of charge.
That's it, exactly. They prevent the voltage from collapsing when you have a massive high-frequency AI workload. Without them, the chip would just slow down or crash.
Okay, that gives us the foundation. And here's where it gets really interesting. Let's talk numbers. The PPA performance, power, and area for N2 compared to the current N3E node.
Right, so the data shows N2 is all about efficiency. The speed gain is, it's noticeable but moderate, maybe 10 to 15% faster at the same power level.
So not a huge frequency boost.
Not primarily. The major story is power. We are seeing a massive 25 to 30% power reduction when operating at the same speed.
That 30% power reduction,
Yep.
That's the golden ticket for data centers, isn't it?
It's the only way forward. I mean, for a company like Nvidia, a 30% reduction is the difference between a manageable data center and a power-hungry monster. It directly addresses the heat crisis in high-performance computing.
Okay, so what about density? How many more transistors can they pack in?
Well, for pure logic, it's a healthy improvement, about 1.2 times the density. But the overall density for a mixed chip, with logic and memory, is only about 1.15.
Only 1.15x. Why the slowdown?
This points directly to a major constraint, something they call the SRAM wall.
The SRAM wall.
Yes, SRAM is the memory that makes up all the high-speed cache on a chip. And while the logic transistors are shrinking, the basic SRAM bit cell structure is not.
Wait, the cache isn't getting smaller.
Barely. The bit cell on N2 is almost the same size as on N3. And since modern chips are often 40 to 50% cache by area,
That stalls the overall density gain.
it completely stalls it, which forces a huge change in how you design chips. The old monolithic design, everything on one piece of silicon, is becoming physically and financially impossible.
So what's the alternative?
The only way around it is disaggregated 3D designs. You take the large cache blocks off the main expensive N2 die, and you stack them vertically, or you build them on older, cheaper nodes. It's a complete paradigm shift.
Speaking of shifts, let's look at TSMC's roadmap. It seems, well, surprisingly conservative. The first N2 node and its successor, N2P, they both still use the old frontside power delivery. Why?
It was all about risk mitigation. The move to GAA nanosheets is incredibly complex. They wanted to perfect that one thing first. N2P is just a modest 5% tune-up on that.
So they're saving the real revolution for the next step.
Exactly. For the A16 node, which is their 1.6 nanometer class chip scheduled for late 2026 or early 2027, that's where they introduced the final piece of the puzzle.
And that would be the backside power delivery network.
Yes, their version, which they're branding as the Superpower Rail, or SPR.
Okay, for anyone listening, we need to break this down simply. Why is moving power lines to the back of the wafer such a game changer?
Well, think about a busy city street. In current chips, the power lines and the signal lines, which carry the data, are all crammed together in the metal layers above the transistors.
It's a traffic jam. The power trucks are blocking the signal cars.
That's a perfect way to put it. What SPR does is move the power lines entirely to the backside of the wafer. They deliver power straight up through the silicon itself using tiny tunnels.
Which clears up the entire front side.
It leaves the entire front side dedicated just to signal routing. It's like building a high-speed bypass just for power. The result is massive. A16 gets another 8 to 10% speed boost and a 15 to 20% power reduction over N2P.
So by waiting, they protected the N2 launch and then get this huge bonus on A16.
It's a calculated move. Predictable execution is what their biggest customers pay for.
Okay, now we have to talk about the elephant in the room. The cost. Moore's Law was always this deflationary promise, right? Cheaper, faster, smaller. N2 seems to blow that model apart.
It's a financial shockwave. We said the price. N2 wafers are reportedly $30,000 each.
$30,000 for one silicon disk.
Yeah, you could buy a decent car for that. It's a 66% price increase over the previous 3 nanometer node.
So what's driving that? Is it just gouging? Or is it genuine complexity?
Oh, it's genuine complexity. The cost comes from a massive increase in EUV lithography intensity. You need more layers, more exposure time, maybe even double patterning to define those atomically small nanosheets.
So the cost per transistor isn't going down anymore.
It's flattening out or maybe even going up. The new metric isn't cost per transistor, it's value per watt optimization.
LU per watt.
Exactly. They're telling customers, yes, this wafer is 30 grand, but the chips you make will save you so much in electricity and cooling that the premium pays for itself. That's the calculation.
And despite that cost, the manufacturing machine is already running at scale. Where are these being made, and how are the yields?
The primary volume is at Fab 22 in Kaohsiung in southern Taiwan. And what's really impressive are the yields. Reports indicate that N2 logic yields have already hit about 70%. 70%. On a first-generation architectural shift like GA. That's stunning.
It's a competitive chasm. For comparison, you hear reports that competitors like Samsung are struggling with 2nm yields down around 40%.
Wow.
That predictable execution is why N2 capacity is already fully booked through the end of 2026. Price doesn't matter when you're the only reliable supplier.
So who's in this exclusive Angstrom club? Who has to buy these $30,000 wafers?
Well, it really boils down to a duopoly of power efficiency demand. Apple and Nvidia.
Let's start with Apple.
Apple is the strategic anchor. The A20 chip, which is destined for the iPhone 18 Pro in 2026, will be the first commercial device. For them, that 30% power reduction is essential for thermal management.
To keep the phone from getting too hot while running on-device AI.
Exactly, for all those Apple Intelligence features.
And what about Nvidia? What problem does N2 solve for them in the data center? They're the volume driver. The next-gen Rubin GPU platform, the R100, is designed around N2. For NVIDIA, N2 solves the power wall. They're designing chips that push past 1,000 watts.
1,000 watts.
If you can knock 30% off that, the operational savings across hundreds of thousands of GPUs are just enormous. The N2 premium is a rounding error compared to that.
And AMD is using it too, but with a different strategy.
Absolutely. A very clever chiplet strategy. They're using N2 only for their peak performance Zen 6 CPU cores. But they keep the I/O and cache dies on cheaper, older nodes like N3 or N6. It's how you get the N2 benefits without a massive, bank-breaking, monolithic die.
This shift to modularity brings us back to packaging, the so-called second half of Moore's Law.
Correct. N2 absolutely relies on advanced stacking to survive that SRAM wall we talked about. TSMC is using its 3D fabric suite. That includes CoWSL for connecting the N2 dies to high bandwidth memory.
But the key fix for the SRAM crisis is something else.
It's SOIC. System on integrated chips. That's their bumpless stacking technique. It's the primary architectural response to the SRAM wall. It lets you stack cheaper cache dies made on an older node directly on top of the N2 logic.
You're literally patching the density hole.
Yes, patching the hole left by the failure of 2D SRAM scaling.
But all that density creates the next barrier, the thermal wall. When you have over 1,000 watts of heat in such a tiny area, how do you cool it?
Yeah, traditional cooling is useless. The heat flux is becoming untenable. The solution, which has to mature alongside N2, is direct-to-silicon liquid cooling.
So liquid cooling right on the chip itself.
Literally etching tiny microfluidic channels pipelines for coolant directly into the silicon, just microns away from the hottest spots. It's the only way to manage this without the chips melting down.
Looking at the competition for a moment, it's a triopoly, right? TSMC, Intel, Samsung.
Yeah.
But it sounds like it's more about trust than just marketing claims.
That's the heart of it. Intel's 18A node is very ambitious. They're introducing GAA and backside power at the same time.
Getting a jump on TSMC's A16.
Right. But TSMC's N2 still has a significant lead in fundamental transistor density. And more importantly, that stable, high yield, that 70% figure.
And that's what customers trust.
That is everything. When you compare it to Intel's reported 55 to 65% or Samsung's struggle around 40%, you see why everyone lines up at TSMC. The difference between a 70% and a 40% yield is life and death for a product.
So let's wrap this up with the financial implications for TSMC. It sounds like they're about to reap the rewards.
It's a financial supercycle. Analysts are forecasting their annual revenue to blow past $100 billion in 2026.
Wow.
And EPS growth of nearly 50%. Critically, because of that high N2 pricing and mature N3 yields, their gross margins are expected to approach or even exceed 60%. That is the definition of a market hegemon capitalizing on a technological lead.
So to sum it up, this has been an industrial triumph. TSMC solved the leakage crisis with GAA nanosheets, securing the efficiency needed for the AI era. But it came at the cost of the old economic model, ushering in the $30,000 wafer.
And the value per watt optimization makes that cost non-negotiable for the biggest players. But, if we connect this to the bigger picture, you have to look at the risk.
Go on.
The global economy's entire AI engine, built on this N2 production, is heavily concentrated in Taiwan, Kaohsiung, and Hsinchu. This geographic concentration makes the whole value chain incredibly vulnerable to regional instability in the Taiwan Strait. That political risk is the single largest discount factor on the value of this entire industry.
That really puts the fragility of this amazing achievement into stark relief. And since N2's density is stalling at the cache level, forcing designers to stack SRAM vertically with 3D packaging, the final question for you to think about is this. As the cost of a flat transistor skyrockets and 2D scaling hits a wall, is the future of processing defined more by who can master the complexity of vertical stacking than by who can shrink the horizontal transistor?